Well, let me first thank IAS for arranging this symposium, and I think that gave us a chance to talk with you. My talk is basically on laser impacts on material science. So I'm just going to give you some materials randomly selected so that we can have a discussion at the end of the talk. Okay. And I'm not going to be able to match Professor Cohen's talk, but I have more color slides than he does. And well, anyway, we're talking about coherent light source and the impact of coherent laser light on material science. And my selection of materials will tend to be random, incoherent, but this is the kind of talk that I can give at my age. And so there was always the saying that old laser physicists never die, but they just become incoherent. So for the color slides, I think the first slide is meant to be turned on the new year of next year. Okay, and so if I know how to turn it on, how come? Oh no, that I see. Okay, that's the one. Okay, all right, yeah. Okay, so that's for next year, the year of light. And you probably all know laser spectroscopy has impacted many fields, and it basically flourished with advances of laser techniques and nonlinear optics. And that allows us to have many techniques for material studies that do not exist before. And as a result, what did I do? As a result, provided revolutionized many disciplines of science. And in particular, we talk about the field of atomic and molecular sciences. And that leads to many Nobel Prizes, starting from Brombergen, Shallow, and then other Nobel Prize laureates also contributed to the field. Lamb, Ramsey, Henge, Kohen-Tanucci, Hall, Steve Chu, and Ames as well. Okay. So this is obviously a very successful area for laser science. But for condensed matter science, we have to scratch our head and say what laser spectroscopy has done to us. So here we first talk about why laser spectroscopy is so useful. Well, this is because all these wonderful characteristics of lasers, for example, it's a very highly directional beam with a spread angle so small, of the order of 0.01 degree, and it can be very high intensity, up to 10 to the 24 watt per meter square from a tabletop laser. And that high intensity can break down anything almost, get you to the nuclear physics regime. And then the pulse width can be as short as 50 attosecond, that's 10 to the minus 18 second. If you talk about the width in space, the pulse width is 1.5 nanometer width. That's 3 orders of magnitude smaller than your hair. Right? And if you talk about the line width, the spectral line width of the laser, delta nu over nu, delta omega over omega, is about 10 to minus 15, or less. And it has a wide tunability from far infrared all the way to soft X-ray, or even more. So you can see, because of these great characteristics, you can have all kinds of novel spectroscopy techniques. And we already know it has done great in the field of AMO. But what has laser spectroscopy done to condensed matter? So here I just focus on condensed matter applications of laser spectroscopy. And the first thing is, it gives you this dramatic improvement on the sensitivity of the conventional optical techniques. Well, we have optical techniques before laser, but now the sensitivity was much, much better. For example, the absorption, luminescence, scattering, and so on, the sensitivity all got increased by many orders of magnitude. Okay. And for example, terahertz spectroscopy. In the past, we called it far infrared spectroscopy. In order to measure the superconducting gap in the far infrared, it was a tremendous effort. But now, with the available terahertz source and detection scheme, we are talking about measuring much more difficult terahertz experiment or far infrared experiment. Measuring superconducting gap is a piece of cake. Okay. So I'm going to give you a few examples on that, but then the laser spectroscopy for condensed matter is, if I consider biomaterials, also condensed matters, then we know that super resolution microscopy or other kinds of microscopy have led to great advances in biology. And then we can talk about many different nonlinear optical techniques. So, for example, wave mixing and the stimulated scattering that can be used as spectroscopy technique, and multiple resonance and the coherent transient and so on, the ultra-fast spectroscopy. So I'm probably just going to focus on two. Okay. So let me give you a few examples on the improvement on conventional techniques. And here is a list. In the past, without laser, we're talking about measuring refractive index change due to absorption or transmission is of the order of 10 to minus 4. Now we can easily get to 10 to minus 7. Okay. For luminescence, in the past, we could see luminescence from perhaps 10 to the 6 molecules. But now we could see from single molecules. For scattering, in the past it's very difficult to collect the scattering of light. I always remember that Raman first did the Raman scattering on the boat using sunlight. And of course, it took him the whole journey from India to England to measure the Raman scattering of some organic molecules. But now we can do Raman scattering from single molecule. And then terahertz spectroscopy, I already said, it was very difficult in the past, using bolometer, so on. But now it's very easy. So a few examples of how the improvement of the technique is. The first example is the famous example now, because Monod got the Nobel Prize for that. And what he did was when he did this work at IBM, and he was thinking of studying using dye molecules for optical memory and storage. Okay. And so he did the whole experiment at very low temperature. And this particular molecule, pentacene, happened to have very strong absorption coefficient. So for a single molecule buried in a solid, the absorption coefficient is 10 to the minus 4. That is alpha times the distance of the whole sample. And in fact, 10 to the minus 4 is pretty easy to detect. And so in his case, because of the background and so on, he had to use double frequency modulation to get the sensitivity up and so on. But he did observe the spectrum of the single molecule, which is seen here. Oh, this is the simulation, and that's the experimental result. So he succeeded the first measurement on single molecule. But of course, if we are in spectroscopy, we know this is a stupid way of detecting a single molecule. If you just shine light on and look at the luminescence, the sensitivity is much higher to detect that single molecule. Okay. So, of course, that was realized very soon, and that's in 1999. They did the luminescence from single molecules, single biological molecules. And you can see every peak is a single molecule. So you can now easily do absorption spectrum or absorption spectroscopy on a single molecule. And you can consider a carbon nanotube as a single molecule. Okay? And in this particular case, Fan Wang's group did this so-called polarization-dependent absorption spectrum. And it's very easy to see why the sensitivity can be high, because in this case, the carbon nanotube is lying on a substrate. And therefore, when you do the ordinary absorption spectrum, you will see a lot of scattering from the substrate. And that's a huge background, making it very difficult to image that carbon nanotube. But clearly here, this is the electron microscopy image of that tube. And now with the optical microscopy, you can see that same tube. How does he do that? Well, you have two polarizers. This is the input polarizer. That's the analyzer. And so if you shine the light going through this polarizer, then the light is polarized this way. And the light reflected from the substrate has the same polarization. Therefore, in the reflected light will be completely rejected by this analyzer if this analyzer is at the cross position. But the refraction from the tube, because the tube is anisotropy, favorable polarization this way, you'll find the refraction light from the tube is mainly polarized this way. And therefore, the refracted light from the tube will be leaked through this analyzer. Okay? So that makes the detection of that tube very easy. And you can increase the signal by slightly tilt this analyzer away from the cross position. And that's the heterodyne detection scheme, making the signal much better. Okay? So this is how they did it. And you can easily see that as delta decreases, the contrast increases. And you can therefore see the spectrum of a single nanotube. And from the spectrum, you can identify which tube you are dealing with. And 26 are the chiral indices of the tube. So that's one example showing the sensitivity of absorption spectrum. And then you can also do the scattering, and it's called a Rayleigh scattering. That is when you have the incident light in resonance with a transition, then the scattering increases tremendously. And that, therefore, you can use that as an excitation spectrum and detecting the transition of a single tube. And again, by this means, you can see that the image of the tube from the scattering. But in this particular case, the tube has to be suspended. Otherwise, you have too much scattering from the background. Okay. So again, from the Rayleigh scattering spectrum, you can identify this is a metallic tube and this is a semiconductor tube. Okay. And then you can also look at the Raman scattering of a single nanotube. And that is the so-called breathing mode. This tube go up, go like that. And you have the G mode, which is the zone center phonon mode. Okay? So again, even Raman scattering can be seen on a single nanotube. And then we can even do terahertz spectroscopy on graphene, which is a monolayer. And the interesting part of this is it's a two-dimensional free electron gas or free carriers. And there is a difference between 2D plasmons and 3D plasmons. And you can see that carrier density with as a function of the Fermi level, somewhat different. And so is the Joule conductivity. And the plasma frequency is non-proportional to square root of the carrier density instead of proportional to the carrier density. Okay. And there's a K vector coming in. And if I have a strip or a finite dimension in that K direction, then it forms a standing wave, and there's a plasma resonance. Okay? So this can all be observed easily now with terahertz spectroscopy. So here's the result showing that if you have these stripes of graphene, then with polarization along this direction, basically we don't have any boundary conditions. So we have the ordinary, the 2D plasma response, which looks like this. Experiment and theory fit well. And then if you talk about polarization in this direction, you see the boundary condition for the stripe, and therefore you have a plasma resonance showing up. And that plasma resonance will, of course, depend on the width. So when the width changes, the peak shifts. And it also depends on the carrier density, which can be adjusted by gating the graphene. And so as a result, you can see that when you change the carrier density, the peak also shifts. So again, this shows that this even the so-called far infrared or terahertz spectroscopy can be easily done on a single monolayer. So applications to biology, that seems to have more effects or more influence. Of course, you heard about optical tweezers, that the laser light focus on a ball, you can pull the ball, but if the ball is attached to a biological molecule, then you can stretch the biological molecule or move it. Right? And we have all kinds of nonlinear optical effects, like second harmonic generation, two-photon excitation, and so on. And they can all be used for different applications in biology as optical microscopy techniques. And then, of course, you heard about the super resolution microscopy, and Michael Loy is going to give you all the details. But here, the well-known two-photon fluorescence confocal microscopy. And in the past decades, biologists used this technique a lot to study the biological systems. And here you can see the neurons, and then the dyes that allow you to see the two-photon fluorescence. Is now the famous one is now the green fluorescence protein that got Shen the Nobel Prize. And super resolution microscopy. And here you probably at least heard about it, and if you haven't heard about it, you will hear about it from Michael Loy. There are the technique of so-called STED, stimulated emission depletion microscopy. PALM is photoactivated localization microscopy. And then STORM is actually the same as PALM, but it has the name stochastic optical reconstruction microscopy. So let me just go very quickly through these principles. And the STED principle is very simple. If we look at this diagram, if you excite the molecule up, it can quickly relax to the lowest excited state and then fluoresce down. This fluoresce down, it can be stimulated, or it's called stimulated emission by Einstein, down to the ground state. So if you shine in a light, then the fluorescence can be much faster. And so as very quickly, the excited state will be depleted, and there's no more fluorescence. Okay. So this is the technique Hale used. So for example, you have a beam focal spot like this, and then the whole area is supposed to fluoresce. But then you make another beam which has this particular frequency to make it stimulate emit. But you make the beam in such a way that it has a hole in the middle. And this is called bezel beam, bezel profile beam. And by doing this, then you see all the red part will see the stimulated emission. And that's going to quench all the fluorescence of molecules in this red region. Only the green region will still have fluorescence. Okay? So this is there for the picture. If you don't do this bezel beam stimulated emission, you will get this picture. But if you put the bezel beam to stimulate the fluorescence, then you will get an image of fluorescence point like this. And in principle, there's no limit to how small it is. Okay. So this is a very simple scheme, but it's a great idea. That's why he got the Nobel Prize. Okay. Then there's Batik's idea, and it's a PALM or STORM. And again, the idea is quite simple. If you have a point source, coming from a single molecule, so it looks like just a point source, very, very small, then the fluorescence image you will see from the microscope will have to be diffraction limited. And that means the image is big, of the order of wavelengths. Okay? But then if you plot out the profile of this image, it will look like a Gaussian profile like this. And with that profile, if the intensity, the signal to noise ratio is good, you can always find where that peak is. And that peak must be the position of that point source. So that's the way you can find the point source to a accuracy in position of less than 10 nanometer. But then, if you have two point sources, sort of like 10 nanometer apart, if you just look at the fluorescence from these 2 point sources or 3 point sources, you will not be able to distinguish them because the image you get is just like that, a blur dot. On the other hand, if you can somehow make these point sources light up or fluoresce separately in time, then you can have each point source appear at one time, and then you can put them together and you can see the 3 point sources clearly separated. Okay. So this is the idea, but the idea needs another ingredient. That is, you have to find molecules that allow you to light up at separate times. Okay. And that turns out it's the very interesting kind of molecules called photo-switchable dye molecules. And the idea of these molecules, you can excite the molecules to the excited state, and then it can fluoresce. Or part of the probability will go to relax to a dark state. And if the molecule relaxes to the dark state, then it will stay there forever and will not fluoresce anymore. But if it comes back to the ground state like this, then it can be excited again and fluoresce again. Okay. Now, with these molecules, if you pump hard enough for long enough, eventually they will all end up in the dark state. Okay. So now if you have all the dye molecules spread out in the plane, and they are all pumped into the so-called dark state. So they are all sort of not fluorescent, even you try to excite it. But then you can send in some other frequency light, say green light. You shine the green light up to another state, and then the molecules could relax down to this bright state, ground state. Well, how many molecules will end up in the ground state? Depending how strong you pump with the green light. So if you pump very hard, of course, many molecules will go to the ground state. But if you pump lightly, only a very small fraction of these molecules will appear in the bright state. So that's exactly the technique they used, because now they can say initially all the molecules are in the dark state, then I make some weak green excitation and make fraction of the molecules back to the bright state. And now these molecules in the bright state can fluoresce when you excite with the red light. Okay? But since they are only a very small fraction of the whole molecules, they are likely to be very far separated. So in one time, you have this set of molecules light up. Then next time, you have another set of molecules light up. So they have all these photo-switchable molecules light up at different times. And that's exactly what we want, to be able to separate the two the different point sources. Okay? So this is the simple basic idea. And you can see that if you have whatever these protein filaments are, and they are all labeled tight, closely, with these photo-switchable molecules. Then you do this kind of excitation. This set of dye molecules on these filaments light up. Next time, this set of molecules light up. Next time, this set of molecules light up. Then next time, this set of molecules light up. Then you just superimpose all these images together. You find this image, which is super high resolution, because the points can be separated by less than 10 nanometer. So this is the picture. And let me give you the most recent biography of Eric Betzig, written by himself. Okay. So you see, he's now a group leader at Genelium Farm, which is a Harvard Medical Institute, working on neurons. But I show you that in 1993, he was the first to image fluorescence molecule at room temperature. Now, I don't know whether it's right or not, but that's what he said. Okay? 5 years earlier than Moner. And measured their positions at the nanometer scale. Okay? Tiring of academia, he resigned and published the concept that would become localization. Oh, sorry, what do I do? And published the, where am I? Tiring of, the concept that would become localization microscopy while unemployed. Okay, so he was not employed. He was at Bell Lab, but then he quit. Huh? No, later. He then served as the VP of his father's machine tool company and developed a high-speed motion control system. But that technology apparently didn't work, so the company failed, and he was left unemployed again. Okay? And while he was unemployed, in 2005, he and his fellow Bell Lab expatriates, Harold Hess, used this photo-activated fluorescent proteins to bring super-resolution localization microscopy to reality, building the first prototype in the living room of Dr. Hess. So this is a Nobel Prize done in the living room, not the garage, in the living room of someone. For this work, he got and so on. Okay. So, but the person who actually made super resolution microscopy accepted, not accepted, but sort of popular in biological community is Xiaowei Chong. And I got all these slides from her. So it's the first-hand information, okay? And these are, this is the old conventional microscopy picture. And this is coming from Storm. It's the microtubulars. And then she felt that 3D image is more important than 2D image. And she had a very simple idea that in order to get 3D image, all you have to do is insert a cylindrical lens in it. And with the cylindrical lens, then you have image at different depths, as you can see here. And then the picture can give you a 3D image. Here the colors represents the different depths. Okay. Again, these are microtubulars. And then looking at actin. Actin is some protein filament, and they sort of wrap around in these neurons or the biological species. And here is the actin in dendrite. What is dendrite? I'll show you later. And this is the actin in axon. Axon is the connecting rod or pieces between the synapses. Okay? And here you can see that there are these sort of, something wrapped around this rod. And you can see the 3D picture shows it's like a ring around a rod. Okay. And so the picture that they came up with is ordinary. If you go onto the Google image, this is the kind of picture for a typical neuron. And here is the axon. And the axon, what people imagine was like this. And this is the dendrite at the end. So now with her high resolution, super high resolution picture, they can come up with a better model. And that is the axon and the rings. The rings is the actin. Okay. So this is remarkable. Periodic structures, and you can do the calculation with pseudo-potential. So it was said by our biological colleagues that this is the breakthrough in neuroscience in the past 50 years. So that's amazing. I really like this picture. It's so clear, so clean, and it's just what physicists love. So on the other hand, Eric Batek and his wife are doing adaptive optical microscopy, and the principle is very similar to the astronomic, so-called laser star, adaptive optics for astronomic telescope. And here, again, as you see that ordinary microscope can focus down to the target and look at the image. But if you have aberrative material in between, then the wavefront will get distorted. So now if you somehow, before the light come in, you make the wavefront distortion to compensate what the light will get in the medium, the distortion the light will get in the medium, then you can again focus it to very tight spot. And the reverse is the process that you can get the image clearly by phase compensation. Okay? So you can see that, again, in the ordinary microscope you get this, but with this is in the beads in water. And water gives you the aberration. But then with the adaptive optical scheme, you can get clearly the beads image. And that's the three-dimensional image. Again, you can see much clearer image in the depth. The reason they are developing this is because they are in Janelian Farm. The whole institute is almost all working on neural system. And so they want to have the microscope to be able to look at the neurons in living animals. And the neuron tends to stack up into layers. And when you want to see how the neurons function, you need to see all these layers, how they function. They are triggered, and function. But the microscope is, for the lower layer of the neuron, if you cannot see them, then of course you don't really know how they are triggered and they function. So that's why they are developing such a microscope. So that is our microscope. And, I'm okay, right? So, okay, so now go to more condensed matter, but I still cannot avoid microscopy. And for many nonlinear optical techniques, you can find a lot of applications, and four-way mixing is one of the techniques that finds a lot of applications. And here I'm just showing you the application on microscopy, and this was done by Sunny Shea at Harvard. He developed this CHKUST microscopy because in microscopy for biology, we see that we always need label dye molecules. And if you put labels on the biological molecules, there's always the question whether they change the behavior and so on. So you would like to have label-free microscopy. So that's actually a challenge. If some of you can develop a label-free super resolution microscopy, I think you have a big chance of getting Nobel Prize within 10 years. So here is a label-free CHKUST microscopy, and the CHKUST process is like this. You pump, you come out so that you can see the vibrational resonance, and then you detect the vibrational resonance by shining a probe beam, and you get this anti-Stokes output as a signal. And this is the microscopic picture of this animal, the worm. And this is a slice of CH2 stretch vibration. CH2 has symmetric vibration and anti-symmetric vibration. Okay? And that shows the lipid drops in this animal. And then this is the three-dimensional buildup of the image from many slices. And then I would like to talk about the sun frequency spectroscopy. And as you know, that often we have many nonlinear optical phenomena, but the complicated phenomena hardly find good applications. It's always the simple effect, a simple process that can find you more applications. And that is true here. Sun frequency is actually three-way mixing instead of four-way mixing. And three-way mixing is always easier than four-way mixing. And then you see that for the three-wave mixing nonlinear process, we have a very simple rule that if the medium has inversion symmetry, that process is not allowed under the electrodipole approximation. And that's why if you have a medium like liquid or polymer or solid with inversion symmetry, this particular process is not allowed in the bulk. But at the surface, that symmetry is always broken. And therefore, you may find that the surface response tends to dominate. And if the surface response dominates, then I can use the signal to find the surface structure of the medium or interfacial structure. Okay? So that is the idea, to use some frequency spectroscopy to study the surface structure or to find the so So I'll give you an example how surface specific it is. For example, if we have a medium, silicon dioxide with so-called hexadecane, which is long chain molecules like this, and you try to do infrared or Raman measurements, you find the signal is very strong because it's dominated by the CH stretches of this long chain. Okay? But if we look at our some frequency spectrum, it's almost nothing. Why? Because there's very little broken symmetry. On the other hand, if I put one monolayer of so-called silane, it's this thing. It's a long chain molecule, but only one monolayer. But with that one monolayer at the interface of these two, you see very clearly the CH stretch signals. Okay. And for double check, we replace this HD by CCl4 that has no CH stretches. And so if you think that the signal is coming from the bulk here, we will see very different spectrum. But in our case, you see the spectrum is very similar. So obviously the signal is coming from that one monolayer. And that's highly surface specific. Now, considering many water interfaces, they are all very important for various applications. And you find that for vapor-water interface, these are the OH spectrum, stretch spectrum. This interface has this spectrum. Silane water interface looks like this. Quartz water interface, this is hydrophobic, this is hydrophilic. Looks like that. They're all very, very different. Indicating the water interfacial structures for different cases are very different. And you look at the polymers. We have different kinds of polymers. Some are low density, polyacetylene, and then ultra high mass weight polyacetylene, and commercial that you can buy. These different polyacetylene. You find the IR spectrum look very much the same. Raman spectrum look very much the same. But you look at the some frequency surface spectrum, they are very different because the structures are different. Okay. And so many other applications that we can use this so-called surface-specific techniques. For example, we can look at the surface magnetization, which is different from bulk magnetization in general. We can look at topological insulators. The surface and bulk are different. And we can look at the surface, and we can also look at the bulk at the same time by doing transmission. And we can look at the surface-induced structures and properties. For example, these days, people talk about surface-induced superconductivity. Okay? And that we could use optics to look at it, surface dynamics too. And actually, we can also do some frequency microscopy or second harmonic microscopy. It has advantages over the two-photon microscopy because we don't need label. The only problem with this nonlinear microscopy is the sensitivity is not good enough. So making super resolution very, very difficult. So when am I supposed to stop? Just give me a time. I have to cut some. 10 more minutes? Okay, sorry. So one is stimulated Raman spectroscopy. We talk about incoherent Raman spectrum, Raman scattering, but we can also do stimulated Raman scattering. And in that case, let me just quickly say that you look at this process. If we shine in both omega 1 and omega 2, then you'll see omega 2 is going to see the gain. And if we have, for example, benzene as a medium, then we can easily calculate from the Raman cross-section what the gain should be. And we find that the gain is 1 per wave number, per centimeter, if the intensity of this pump light is 1 gigawatts per square centimeter. Okay. Now, we can always have higher laser intensity. So if we increase the laser intensity to 10 to the 11 watts per square centimeter, then we can have a gain of 100 per centimeter. And again, for material like benzene, we can easily detect a gain of 10 to minus 6. So that means we should be able to detect the Raman spectrum of benzene in a solution of 10 parts per billion. So the sensitivity is actually higher than the spontaneous Raman scattering. And with this, we can do excited vibration in the excited electronic state, because then you can pump the light to the excited state and then look at the Raman scattering from the excited state. Even though the excited state population is low, I still have the sensitivity to detect it. Okay. And then we can see, for example, the time resolve Raman spectrum when you photo-excite rhodopsin molecules in your eye, and it will have the conformational transformation from here to here, and you can see from the vibrational spectrum how it changes over. Well, but I want to say that Raman scattering these days is already so sensitive. That is, if you go to a storage room of chemical materials, you see all kinds of chemicals, the benzene, ethanol, water, chloroform, all these salt liquids, they are all transparent, white. So you'll never be able to tell unless you open it and then you try to analyze it, then you can find it, or you rely on the labels. But these days, you can have a small Raman spectrometer with a helium neon laser or a pointer laser, and just go there and shining on the liquid, looking at the Raman spectrum, you can identify which species that liquid is. Okay? So it's that sensitive. But now we're talking about orders of magnitude improvement on the sensitivity of that kind of scattering. And then we can even do better. And, let's skip this. And this is the, you can use stimulated Raman scattering for microscopy. And that also is very, very interesting. But now you can use so-called optical combs. Optical combs is you have equally spaced frequency, and that got Ted Hensch and J. Hall the Nobel Prize. And now you can use two optical combs with different frequencies, and shining on the medium, let them beat, with some temporal lap, and let them beat, and they'll get the interferogram like this, and then you do the Fourier transform, and you can get a spectrum like this. And the sensitivity is another 2 orders of magnitude better than the stimulated Raman scattering I just mentioned. So a spectrum like this from an organic molecule takes 14.8 microseconds. So you can see how sensitive that is. So this is, again, this is the work of Ted Henge. And for condensed matter. Now, you heard about that, we can measure current, and we said you have quantum Hall effect, or have Hall effect, spin Hall effect, and so on. The measurement was always done as the end result. You measure what the current coming out, or how the current meter shows, and so on. But do you know how the charges or the current actually move in the material? Very few people would do that, right? But now it's possible using nonlinear optical technique, because if you have a current in the medium, then it induces an asymmetry. And that asymmetry is going to give you the second harmonic signal or some frequency signal. So the theory is like this. You have the second order, say second harmonic generation. You have this induced polarization like this, and this part is coming from the asymmetry. Now, of course, you would say the current is coming from the applied field. But this applied field in metals or semiconductor, the field is very small because there's a current going. So the distortion coming from the field is small. But if you have a current going in the medium, then in the band structure, the population must have this asymmetry. And that the asymmetry of the population distribution or electrons the gradient will give you a current. But it is this asymmetry that is the source of the second order nonlinearity. So with this, you can actually detect, for example, charge current or spin polarized current and pure spin current, depending on the polarization of light you use. You can detect different components. So for example, here you can see that there's a gap, there's current flowing, and you can map out the current in that gap. And this is the time dependence in a particular experiment. And you can also detect the spin current, pure spin current. And then we talk about optical rectification that goes like this. If you have a short pulse going through a nonlinear crystal, it can be rectified into a pulse like this. And that's actually the idea of terahertz generation. But this is generating an electrical pulse. How about generating a magnetic pulse? It's also possible. And again, the idea is very simple. We know, for example, here, we usually have the Zeeman degeneracy to begin with. Let's consider an atom for simplicity. Now we shine a light on. If the frequency is less than this transition frequency, the AC Stark effect pushes the two states apart. But if I use circularly polarized light, then only the two states that connected by this light, will be pushed away. The other two Zeeman states will remain. So immediately you see from this diagram that the Zeeman states are split, and therefore it creates a magnetization. Okay. So with this, you should be able to see this induced magnetization by the pulse. Now, I'm showing you the energy description, but also the optical light can mix the wave functions. And so one is corresponding to paramagnetism, the other corresponds to diamagnetism. But anyway, the magnitude of this split is actually related to the Faraday effect. And this particular process is actually just the inverse Faraday effect. So if you know the Faraday rotation, Faraday coefficient, you can calculate what is the field you can induce. So for example, we can have 10 to the 4 Gauss induced by something like 10 to the 8 ESU, that's 25 gigawatts per square centimeter. And you can induce a 1 tera Gauss, what's that? No. Anyway, 10 to the 4 Gauss of field. And this is coming from a femtosecond pulse. Now, how useful is the femtosecond magnetic pulse? I don't know, because the magnetic response always seems to be very slow. So perhaps it's useless. Okay. But anyway, it's fun to have such a short magnetic pulse. And one application was you shine in such a pulse, create a pulse magnetic field, and then the medium has to respond. So the spin starts to precess, and you see the precession. And that precession of the magnetization can be detected by Faraday effect. Okay. So this is probably important to talk about. What are the future prospects? Well, we have new techniques already developed or to be developed. I already talked about terahertz spectroscopy. Sorry. But now we can generate far infrared radiation or terahertz radiation with 10 to the 7 volt per centimeter. That's so large, you can easily see nonlinear optical effect. Okay? Not only just an intense source for spectroscopy. We can have attosecond X-ray pulses coming from high harmonic generation. And we're talking about attosecond X-ray. So obviously you can look at structural dynamics with that high time resolution. We can have optical frequency combs. Again, the combs are frequency combs. That each line can have line width of the order of hertz. Okay? And we're talking about going to soft X-ray all the way. So the resolution, the spectral resolution, is much higher than what you can think of. And obviously it's useful in atomic physics for precision spectroscopy. I don't know, in condensed matter physics, I think when you look at this photo emission, having a spectral resolution less than 1 eV, you can generate a lot of interesting effects and so on. But here we're talking about at least 10 orders of magnitude higher spectral resolution. Okay. So what is the use of condensed matter? You can imagine. Okay. Sub-picosecond electron pulses, where you can easily shine a femtosecond pulse on your target and emit electron pulse of the order of femtosecond. And then you can use the electron beam, the pulse electron beam, that has sub-picosecond resolution to do diffraction or microscopy, electron microscopy. So that's another new technique. And then we have the accelerated electron pulses. There are many different schemes of using laser to accelerate charged particles, and especially electrons. And let me just give you a quick I'll skip these. Okay, this is one version that just came out. The scheme was known, but these beautiful pictures came from the recent issue of Nature. And what it does is you use laser to create a long column of plasmas. And then you shine in a ultra relativistic electron pulse that creates this so-called plasma wake. That means you have a strong field in this region. The field is given here. So in this particular region, if you have electrons, then the electrons will be pulled by the field and accelerate. So with this pulse going on, the electrons will follow and get accelerated. So that means if you shine in another electron bunch going into this region, then these electrons will be accelerated. How good it is? You can, in this particular case, you can get 4.7 GeV per meter. And that's very high. Other people already had a few years ago, gigawatt per meter. Well, what's interesting is gigawatt per meter, and the synchrotron radiation, the newest synchrotron radiation facility that the people are building is 9 GeV output electrons that generates the synchrotron radiation. And this means that you can do it in 1 meter or 2 meters. Okay. With that, that's the beautiful picture on Nature. Okay. Now, with this, you can imagine that you shine these electrons going through the undulator. So the electron beams will go oscillating like that. And that's exactly the synchrotron radiation way of creating X-ray. But if you can just use the tabletop electron beam in 2 meters, you can do the same thing and give you the hard X-ray radiation. And the cost, I think, is at least 100 times smaller than the synchrotron radiation facility. So that's the hope. Anyway, I think these are the new techniques developed, and the last one was the near-field spectral microscopy, that you can have the tip together with the light shining on a resonance on the substrate, and you can have nanometer resolution also. Now, with all this, obviously, you can have many possible research areas. And one is you can have ultra-fast interfacial dynamics. These are the areas that people can explore. Ultra-fast interfacial dynamics. This is very important for all these devices, photovoltaic, water splitting, and all that. And then you have the laser-induced novel phases and material structure. That is, when you use a laser pulse, you can induce metastable structure, or you may be able to switch the materials to some unknown structures. And then the interfacial structures of nanomaterials have never really been explored. People just assume that the surface is like this, and then start working on the nanomaterials. And spatially resolved transport dynamics. I think when we have all these interesting transport problems, it is finally, it has to be the transport dynamics that you can actually see transport is going. That would be interesting. And then finally, there's this new field called high energy density matter. And that is coming out from the laser fusion project. You can use implosion to press on the material, make it very, very dense. And before you reach the fusion threshold, this high density phase comes out. And it must have very interesting properties because we're not talking about interatomic separation approaching the ionic de Broglie wavelengths and Bohr radius. And the implosion can lead to 100 times compression. And at that density, chemical bonds, all our understanding of material breakdown, I suppose including pseudopotentials. Okay. So this will be a very, very interesting area, a new area of condensed matter. It's related to condensed matter, of course, plasma physics, planetary physics, because the sun is like that, and the material chemistry, because chemical bonds no longer, the concept is no longer valid, so therefore you have to have a completely new picture, and nuclear engineering. Okay, so let me just finish by the summary remarks that we have seen the tremendous impact of laser spectroscopy on condensed matter physics or science, although it's still not as much as AMO, because on AMO there are so many Nobel Prizes given already, right? And there's not one in condensed matter. It certainly affects more chemistry and biology than physics of condensed matter. So therefore, for discussion, I have this question: why the application to condensed matter physics seem to be limited, and optical studies of condensed matter always seem to get less attention and appreciation than transport studies in condensed matter. Okay. Well, my simplistic answer is we need an optoelectronic industry as viable as the electronic industry. Otherwise, we don't seem to have this support. Okay. Thank you very much.
Thank you very much. So we have some time for questions. A bit of time. Hold on, I'll bring this to you. Stay. Good exercise.
Professor Shen, thanks for the introductions. And I'm doing some research in the nonlinear optics, and it's there's also always written in the books that second harmonics generation is involved in the second order nonlinear coefficient, while the two-photon fluorescence is involved like the third order nonlinear coefficient. And it seems like the two process all involves the two-photon process, you know. But why is this the difference in the second order, third order?
Yeah.
Is there? Oh, okay. Another part is there any limit in the symmetries on the material when we apply for the two kinds of microscopy?
Oh, yeah. Okay. For the first answer is, when you talk about they always involve two photons, meaning that you are looking at the intensity. looking at the energy aspect. And the definition of nonlinear order is actually on the response function. Response in the sense the field respond to the, response to the field instead of the signal appears as intensity. We are talking about the final result, what is the response to the applied field. So for example, for the second harmonic generation, we have one field goes up, another field goes up, and then we have the second harmonic field emitted, okay? So from the energy or photon aspect, you have one photon, and coming out, okay? But if we talk about two-photon excitations, we usually talk about the response function. One step go up to the excited state, and to see the response, we have to come down, and two steps coming down. So it's like four steps. The second harmonic case, one step up, another step down. 3 steps. Okay. So you have to think about it, or I can explain to you more clearly later. Okay. And for symmetry, two-photon excitation is, as you said, third order. And second harmonic is second order. Second order has the symmetry that if the material has inversion symmetry, then it's not allowed. But for the third order, we don't have that symmetry restriction. Okay. Because one is third order, the other is second order.
Oh, more questions? Any more questions? Yes, Professor Loy. Hold on.
For the fusion. So, how long does it take before it gets to fusion? How much time do you have to do the experiment?
Oh, no, it's not the question. I mean, there's a range of pressure. If you increase the temperature a little more, or increase the pressure a little more, it will go to the fusion. So there's a range that this high-density material will appear.
So if they make a bomb that the bomb failed to go, that's the same thing, right?
If the energy is not enough to
To
hide the
bomb,
fusion.
yeah.
Yeah.
Close is nuclear. How close is the fusion?
It's always close enough that the government is willing to put money in.
Close enough. So, any more questions? And if you have any questions that occur to you at any time, you're going to be here. Both of you are here for a few more days, the rest of the week, or tomorrow. So you better come.
Afternoon.
Yeah, to find them in the break. Okay, so I'm going to ask you to share the. Oh, let's thank Professor Shen and also thanks Professor Cohen also. Thank you very much.
Thank you. Thank you.